So, hello and welcome everybody to our today's ERCI webinar, Seamless Vehicle Positioning in Rail via GNSS and Ultra-Wideband Sensor Fusion. My name is Rico Siegmund and today, together with my colleague Lutz Hübner, I will guide you through this webinar. At first, I will give you a short introduction about ERCI, the European Railway Cluster Initiative. We are both members of this network. The ERCI is a super cluster of 70 railway cluster organizations all across Europe. And me, myself, I'm from the Saxony cluster in Germany, Rail S. My colleague Lutz Hübner from the cluster from Berlin, Brandenburg. Yeah, together with the ERCI network, we are in the possibility to have contacts about from over 2,000 companies all across Europe in the railway sector. What do we do in the ERCI? Besides these webinar series today, we get our companies the possibility to be visible at European level, to do R&D projects at European level, and also to have partner matchmaking at this level. We also do some bilateral workshops. We have an innovation award at European stage, and we have some task forces for special topics like cybersecurity, multimodal logistics, green sustainable mobility, and human factors. Yeah, that will be in a very short case. What about ERCI? Everyone gets the slides of today from the beginning of ERCI to our today's speakers at the end of the webinar. And now I will start with our first speaker, with Matthias Beer from the company CI for Rail. Matthias is a co-founder and CEO of CI for Rail, and he has a background of electrical engineering at the University of Applied Science in Nuremberg. He has over 20 years experience in the rail industry, working as an engineer, product manager in the product management and global sales at his position with his before company MEN Microelectronics. Yeah, that will be the introduction. And now, Matthias, the floor is yours.
Thank you so much. Good morning, everybody. I'm pretty happy that so many people registered for this webinar. Thanks also to Lutz and Rico for organizing that. I will share my screen now. Give me a second. So, Rico, I hope my screen is visible for everybody, so then we can start.
Yes, you can start it.
Okay. So again, my name is Matthias. I'm CEO of CI for Rail, and this one stands for Computing Intelligence for Rail and Public Transport. Our company is a startup company founded in 2022, and we take care about data-driven added value projects with our customers for rail and public transport. So we collect all kinds of data sources, sensors, and so on, and positioning is simply one of the data sources we take care about. Today, we will talk mostly about positioning and localization. And I'd like to start to introduce you to some guys. I've thought about a lot of people who might have an interest in positioning. And let's talk about Stephanie. She's a tourist. I'd like to introduce you to Eric. He's a businessman. Then we have Peter, the bus driver, Marcus, the train driver. Then a very important person is Isa. She's a dispatcher at a public transport operator and a fleet manager. And we also will talk about Henry, the track worker. And we will talk about how much all of these people have an interest in positioning and localization. So let's start with Stephanie. Maybe this is one where everybody can agree on. When you're a tourist, you need to know, where am I? How maybe can I find a new restaurant? And you typically use maybe your cell phone with that. You maybe use any program app on your cell phone, and this typically is sufficient with a built-in GPS. Typically, you are the user of this positioning information, and that's fine and fair enough. So maybe this is good enough with a built-in GPS. When you are on a business trip, let's talk about our Eric. He might have an interest in, how do I find my customer? How do I get to my business meeting? How can I find the best route without any traffic jam? And he's, of course, also using navigation systems, maybe in the car. Also, these navigation systems today work on GNSS, and they are pretty much sufficient, and they are accurate enough because they are also supported by cartography. So even if you're offline, if you're off-road, the GPS of a car always puts you back on the road because they know where the road is in the card. You're also the direct user of this positioning information, directly you as a driver. Then we find already the first problem. So what about in tunnels? Does it work properly in tunnels? Yes, pretty much, because of the cartography. So these about the use cases for positioning everybody knows. So that could mean, is a standard GNSS not sufficient? When we talk about GNSS, we do not mean only GPS, we also mean all the other solutions from other countries. So GPS, GLONASS, Baidu, and Galileo. And we all know GNSS only works properly with a free site to GNSS satellites. We need at least site to 4 satellites to work. And we also know that GNSS does not work, at least not properly, indoors. In addition, the GNSS accuracy is not very precise. It's typically 2 meters to 12 meters, and really is depending on situations like weather, how many satellites are in view, do we have any reflections from buildings. So the accuracy cannot be guaranteed. Even if you think, if you're an industrial company maybe, and you think, hey, I have chosen a GNSS receiver and it says it's 2 meters secure, then there's always a little bit of a side note with the CEP 50%. And the CEP is kind of a measurement methodology, and it's called for circular error probable. And that simply means that 50% of the measurements are within that 2 meter circle. That's great, but that also means 50% of the measurements are not. So you cannot guarantee high available and reliable 2 meters accuracy. So is GNSS sufficient for our needs in rail and public transport? We don't think so. So let's see what the motivations in rail for localizations are. Here's a little picture of a lot of trains, and you can simply imagine, okay, with a GNSS, I cannot accurately position and localize my train. Who needs localization of a train anyways? The driver, is it really the user of a high precise localization of a train? Yeah, in this case, you can imagine maybe the train driver needs to go to his train, needs to move it, and he needs exactly to know which route to which train he has to do. But more importantly, it's important for fleet managers, for dispatchers, for maintenance managers to identify a train precisely. A second example I brought as a motivation, more and more railway stations, for example, are kind of indoors. Think about Stuttgart. This one is an example from Berlin. Here, there might be a need for ESA, our dispatcher. She needs to know where exactly the train is within the railway station. Has it already left the station? And she always asks, why am I blind indoors? And a third motivation would be, let's look into the future. We are all working on future fully automations of trains, automatic operations of trains. And this implies a very accurate positioning on a train of a train on a track. And it needs to be not even accurate, it also needs to be safe. It needs to be really sure that this train is exactly on that position. This is future stuff, but nevertheless, the train builders today want to know exactly on which track they are. And with a standard GPS, you see the green circle here, you cannot tell if you are on the right or on the left track. When we go into public transport, there is even more motivation for high precise localization. Here's a picture of a typical depot of a public transport operator. And you see there is mixture of bus areas and tram areas. And there is even a mixture of indoor localizations and outdoor areas. And Isa, she's again the most important person here. She has the job to organize her depot of 300 buses and 200 trams. And she needs to plan where to park, which bus, which tram. She needs to plan the drivers, the routes, the charging, the repair, even the cleaning. All that needs to be organized. And if you don't know where your buses are, it's inefficient. When you look at these two pictures, it also gets clear. Peter, the bus driver, he gets the job, go to your bus 358 and go on your route. And he needs to be directed directly to his bus. Yeah, where is my bus? Which one maybe do I need to move first before I can get my bus out? Or other questions like, has it been through the washing lane already? So there's a lot of use cases for automation on a depot. And with companies with this amount of buses, it's essential to localize the buses in detail. And another example of localization in public transport is our Henry. Our Henry is our track worker. He works in the tunnels. Maybe he needs to identify and repair damages within the tunnels, and he needs to exactly know where he is in the tunnel. He wants to document damages, highly precise. He maybe has a tablet, and this one needs to localize itself very accurate, and then he documents wherever a damage is. And in addition, he would like to be safe. Everybody working with him should know where he is to warn him from upcoming trains and things like that. So as a short summary, there's many assets, many items which need to be localized. I made a few categorizes here. In the middle one, these are the obvious ones. We want to localize passenger trains, locomotives, light rails like trams or something like that. But even special vehicles, buses, trucks, or freight wagons need localization. And then when you go more on the depot, you have a lot of equipment as well, which it's good to know exactly where it is, like forklifters, cranes, lifting equipment, but even down to tools, spare parts, load carriers. It's very important to have a clear view of where these are. And on the most left side, there's another group of a highly interest in localization. These are people, individuals. Train operators do have a high interest in helping their passengers, maybe navigating them to their seat in a train. We want to know exactly where rail workers are. Think about our Henry or the maintenance personnel. So all that is kind of a summary of what to localize. When we now talk to Lisa, Peter, Marcus, and Henry, what would they like to see from a today's localization system? They will answer all these items here. They would like to see a high precision and high accuracy localization system. They want to have it high available. It doesn't help if 50% of the measurements are good enough. More than 99% should be highly accurate and precise. We have found out that we need a localization system which is good for indoors and outdoors. It should give a seamless position. It doesn't matter if the train or the bus goes from an indoor area to an outdoor area. I simply want to have one accurate position. I would like to have the direction of a vehicle. Think about Peter. He needs to move other buses first, maybe before he can get to his bus. We would like to have the position in real time, live, every second. And when we talk about rail, a very special thing comes on top. It needs to be robust. It needs to be highly robust, withstanding harsh environments for the rail life, which can take up to 35 years. And as we also find out, a localization system should not only be for vehicles, it should be open also to help for assets and individuals localization. And when we summarize all that requirements, we think, okay, it's not only one technology which could help. We need a mix of technologies. And this is, I'd like to introduce these technologies now step by step. On the most top, okay, let me add a laser pointer here, and I hope you can see the laser pointer here. On the most top, we have the technology GNSS, which helps for auto localization, yes, but we found out it's not accurate enough. So we use a special flavor of GNSS. It's called real-time kinematic, RTK. I will go into a more detailed technology session in a minute. This is for highly precise localization outdoors. This one can even be more accurate by using live correction data. Also here another slide will follow. When it comes to indoor localization, we use ultra-wideband together with our technology partner Pinpoint, and Thomas will explain all the details later in his session. But still, this is not enough to have an always high available and reliable position. We also need some IMUs, inertial measurement units, to do plausibility checks, to do direction detection, data reckoning when it comes to tunnels. We also include a wheel tick input from the vehicle to have more information on mileage, speed measurements, and direction detection. And all that together, fused from different sensor inputs together in one device, creates a highly precise position. And this is called LYVE. Our solution, Localize Your Vehicle. LYVE is an open, and I really mean really open and standardized high precision positioning solution for vehicles, and can also be used for people and assets for a lot of use cases, like in depots and parking facilities, in areas with limited satellite visibilities. Think about the main railway station in Berlin, or in tunnels, but also for the daily operations, indoor and outdoor. The solution is not limited to buses or to trains. It's qualified for both road and rail applications, but it's not even limited to these vehicles. And this is how it looks like. You may have seen this picture already in the registration. On a very simple scale, we have our vehicles, and the vehicles have an orange vehicle component. It's called the tracelet, and this one receives information from satellites, GNSS satellites or ultra-wideband satellites, and calculates its position within this little orange device. So this is a cornerstone of our solution. Localization calculation is done in the vehicle. So it uses on the outdoors the white shown GNSS information. It uses correction data to even improve the accuracy. In the indoor area, in the green one here, we use the ultra-wideband information to localize ourselves. And then the calculated position, together with a wheel tick, for example, will be sent either to internal in-vehicle systems, which may process the position information, or it will send the information directly to a localization system in the depot. All this now we will get in more details. So, but first, 2 slides on technology. I introduced real-time kinematic, and I'm not sure if everybody is familiar with real-time kinematic. Let's start with standard GNSS. We have the satellites, we have maybe our vehicle to localize, and this GNSS receiver on the vehicle receives the codes sent from the satellites, sent by every second, for example. And within when you have a free site to 4 satellites, you get a position and a time. But this one, as we learned, is not highly accurate. So for an example, I made here 5 meter accuracy for this vehicle. If you install a second receiver not far away from the first receiver, you will see a very astonishing situation. Both receivers see the exact same errors and the exact same uncertainties of its position. So we both have a 5 meters inaccuracy of our position, but we have a relative distance to each other of approximately 1 centimeters, because all the errors which appear in a navigation or positioning through GNSS are the same for both receivers, and therefore we can create a relative distance of the two of 1 centimeter. And this one can be used to help us to create an exact position. And this is what real-time kinematic does. We say, okay, we have a second receiver, let's call it here a base station, where we exactly know where it is. We do a lot of effort to exactly define the exact position of that base station, and we don't move it anymore. This is a known position. And our train is still, it's still unclear where he is exactly in a 5 meter radius. But now, since we know exactly where the base station is, it can calculate correction data from its received position to its real position. And this correction data can be sent back to the train, and the train receiver can then also calculate an exact position. This is the philosophy of real-time kinematic. So that means we need correction data from a known position, and then we can, on the train, we can calculate the exact position. And as a second difference from RTK is we do not use the CA codes anymore sent by the satellites, but we use directly the radio waves. These are pretty much the two major items of RTK. The carrier waves are correlated to each other, and we do not use the codes, but a lot of physics in wavelengths and so on. And I've brought a little definition here. And this works fine as long as the distance between the known base station and my moving asset is below 50 kilometers. As more distance I have, as more inaccurate we will get our centimeter-like positioning, of course. Why is there a need for correction anyway? Why do we have such an inaccuracy? Yeah, we have, by GNSS, we have different error sources which lead to inaccuracy. And this is, for example, deviations from the satellites, from the predicted orbit. We have time errors, we have delays in the signal propagation time, and we have signal distortions due to the ionosphere and troposphere. And you can imagine that if the receivers are pretty close to each other, they see the same errors. And those errors can be corrected in real time by these correction data. But real time also means we need to get these information in real time. And there are two ways of doing that. A, we put a local reference station somewhere. You can imagine this might work on a depot. I have a depot, I put one reference station on a very known position, and this can help me as long as I move around on my depot. But for trains which travel maybe all over Europe, it doesn't work because one local reference station would not help. And therefore, there's a second option. It's a network from reference stations, which I can simply access through the internet. These network, it's called N-trip services, and there are several N-trip service providers in the market which distribute correction data once you request them. But keep in mind, this requires permanent internet connection. As a third slide for technology, I started to do some ultra-wideband technology, but I'd like to skip that to Thomas because he's the expert. So wait for the second session here. Good. let's go into the live components. Which components do we need for localization, e.g. in this example, for a public transport depot? So we have the vehicles. That can be buses, it can be trams, it can be locomotives. They will create, they will have a vehicle tracelet on board, and this vehicle tracelet sends position information to maybe a Wi-Fi infrastructure, which is connected to an operator locating system. It uses reference stations, either in a network or a local one, to improve its accuracy. For indoors, we need the green area of ultra-wideband area to localize indoors. And we would like to have a site hub to allow monitoring and maintenance, because we want to see, of course, the performance of the system remotely. And we now quickly go into the different components. So as I said, the vehicle tracelets are installed on a vehicle and need, of course, to be qualified for use in trains and buses. We call that component a tracelet, and it really does the sensor fusion of ultra-wideband GNSS RTK, the wheel tick, the EMU, everything on board in a little component. And it provides a fusion position as VGS84, together with a few more information, and communicates its position either via Wi-Fi or via Ethernet or even via LTE. Here's a few more informations on the tracelet. Since you get the slides, I'm not able to, or I'm not willing to read everything right now. Keep in mind the most essential part, we calculate the position in that little device, not at a localization server somewhere at the depot. For the ultra-wideband, we need the infrastructure components like the satellites and gatelets. These are the green highlighted devices here. And this is for the indoor stationary satellite and monitoring devices. And the philosophy is pretty simple. It kind of copies the GNSS idea of having satellites and a moving tracelet within that area. It copies that philosophy into the inside. More technologies from Thomas. Also a few more details, but given the time, I'm not going in detail on that. The correction data I mentioned already. We have the correction data service network, NTRIP services, and again, it requires permanent internet connection. We will have an NTRIP caster on the site hub. And this is not only, it comes with additional cost. It's not only for the data transmission costs over the mobile network, for example, but also these services are mostly cost money. And this stands against the other option, a stationary reference station, whenever it works on a depot. This does not create operational costs, but of course one-time costs, because this one needs to be bought and it needs to be installed properly. But then there's no internet connection required. To offload our position, there's on a depot, for example, a Wi-Fi infrastructure necessary, and we can work with an autarkic infrastructure for our use case, but also we can use existing infrastructure, which is very often the case. Then, of course, there's the questions, how many access points do we need? And it really depends on the positioning area. Alternatively, we can push the localization information also via Ethernet to vehicle internal systems or via LTE to a cellular network. The site hub itself creates a little bit the maintenance and monitoring entry into such a system. We install a stationary computer, and this allows monitoring of all the mentioned components, doing some alarming when something is not working properly, allowing software updates of all components, inventory management, and also the distribution of the correction data. So one slide more to monitoring and maintenance. Let's go back to Isa. Remember, she's our fleet manager and dispatcher, and she wants to know, she's working for example, she's working for the public transport operator, and she wants to know how the system performs. She wants to know, are all my systems up and running? What's the status of my tracelets, satellites, gatelets? What about the Wi-Fi infrastructure and the edge computer? I will get status. I'd like to know what software versions are installed on which hardware. So I'd like to see inventory management. And I would like to have the chance to compare traces in a visualization tool. Maybe something is in my depot management, it's wrong and the position is wrong. I would like to see what's the reality in a separate visualization tool. So that's what Isa wants to know. But there is also Paul, a new guy. Paul works at the system integrator, maybe a company who's offering the full localization solution to Isa. He signed a service contract and he needs, of course, to know even more. He wants to have everything what Isa wants, but he wants in addition to define and receive alarms, to have the chance to deeply analyze system metrics. He wants to have software and configuration updates remotely for all kind of components. And this is what our system also includes. So I brought you a few demos, which shows where this stuff is already used and how the results look like. So the first demo, it's for regional trains, and this is a very interesting application because it monitors how a train moves into the washing hall. You might think, why is it so important to localize a train within a washing hall? It can be on the track and nowhere else. Yes, but when you think about automation of processes, you would like to identify and document, has the train gone to the washing hall, has it left, when, and so on. And this can all be done by this localization. So on the left picture, you see the washing hall. Here you see an example of a satellite, which is installed on several positions within that indoor area. Here you see the installation of a tracelet. This is, of course, for temporary installation. So this is on the roof of the train, and this is all you need in the vehicle. That's kind of an intelligent antenna with everything to compute the position indoors and outdoors. And here you can see the results. Then the train moves into that washing hall, and you can see a very accurate position in that washing hall. As a second demo, I'd like to reference to Peter, our bus driver, and Isa. This one's a demo on a bus depot in Nuremberg, Germany, where we installed our device on a bus, on an electric bus. And I'd like to show a little kind of movie. So at the moment, the bus leaves backwards the hall. Let me check if I can squeeze. So the bus is now moving forward, and on the right side you can see a video from the driver's perspective. And now the bus is driving a very narrow lane besides the building and the end of the area. You can see it's a very narrow area here in the video, and the bus is really localized in the middle of that lane. So this is RTK positioning with the correction data. And I would like to show you this video because it also shows how when the bus is stopped at the exit of the depot, we move a little bit faster here. So now when the bus needs to stop because there's some traffic jam, and I would like to direct you, there is no hovering around. The bus is totally stable until he moves again. So it's a very accurate position down to the centimeters. Then he drives further. Let me go to the next and last demonstration we have brought. I introduce even a new guy, and this is Hans. And Hans looks for his beer. And therefore, we have installed a localization system in a beverage market together with a good partner in Berlin. And we have installed on forklifters our localization tracelet. And we have installed in the beverage market satellites to have an indoor and outdoor localization and have a seamless localization when the forklifters leave and enter the hall. So you can see the the beverage market here, and you can also see where the tracks are. We go into a little bit more in detail. This is again a movie. You might see this little blue areas here signed in, and this is where this is the localization areas where the forklifters can move around. And we simply defined these to see where we are. I switched to a normal cartography since it's easier to see. And then we start a track. Now we are outside, and the forklifter moves on the outside. He's heading towards some trucks to load and offload some equipment, maybe some beer cans or something like that. You can see very accurately how the forklifter moves back and forward to offload a truck, and he's doing that for several times. It's all outdoors, and it's all giving GNSS information for now. We move a little bit faster because it takes a while until he has offloaded the truck, and now he moves indoors. He heads here's the border between indoor and outdoor, and you can simply see the forklifter enters without any whatever big hump or something like that. So now it's indoor, and now the position is coming from the indoor ultra-wideband information. So it was a seamless handover. You as a user, you don't see any difference. And now the same happens indoors. Some back and forth, some onloading, offloading stuff. So much to the demos. What I would like you to take away are 5 major points. One thing is we have a technology combination, yes, but one technology combination that can localize everything. When I say everything, I mean it's good for vehicles from rail and buses, but also good for assets and individuals because, and this is what Thomas will focus on in his presentation, the same infrastructure can be used for individual localization and positioning. We have a solution which bases exclusively on standards. I haven't spent much time on that, but Thomas will also dig deeper into the standards. So we do not use any proprietary solutions or protocols. And this allows us to have a future-proof and independent solution. A cornerstone of our localization is a decentralized position calculation. So we do every calculation in the vehicle, and that, I think it's clear, it means it's scalable. When you think about the 300 buses on the depot, and you would have a localization system to calculate stationarily the position of 300 buses, it really depends on how many buses are currently on the depot. Since we calculate on the vehicle, it's fully scalable and doesn't matter how many buses are on a depot. We think a remote manageability and maintainability is key because this, of course, reduces the effort and cost for local presence. All in all, the technology mix and the solution we have chosen allows minimized infrastructure indoors. I haven't even gone in detail here. We don't need any network infrastructure indoors. The satellites communicate exclusively via ultra-wideband, so via radio. So it's minimized infrastructure needs, minimized cabling, and outdoors we don't need any infrastructure because we use the GNSS satellites, which are there anyway. And by reducing infrastructure cost, we reduced overall costs and complexity. So summarized, could we help to our guys, Henry, Isa, Marcus, and Peter? I say yes. For Henry, we have a solution. He can localize himself in a tunnel. Isa had the most benefits because she knows how to dispatch and manage their fleet. Marcus and Peter can find their vehicles. Just for Eric, we think Eric is not interested in our solution because he has what he needs, and you can also think the same about Stephanie. She's also good, but I would like to say even Stephanie has a benefit of our localization solution, and this will be part of Thomas' presentation. So thank you so much. I'm happy to answer questions. This is where we are. We are in Nuremberg, Germany, and we will be present at Embedded World in a few weeks and on the IT Trans in Karlsruhe this year, presenting our solution as well, and at the InnoTrans in Berlin in September. So thank you so much.
Thank you, Matthias. And now we have some questions. So I will start with the first one. Are you providing RTK correction service as well, or do you rely on known providers?
We rely on known providers. We do not provide we do not provide this by ourselves. When it comes to a stationary reference station, we can bring this as included in our solution. But we, when it comes to network-based, IP-based correction data, we use services like Sapos in Germany or the uBlock service Point Perfect.
Okay, next question. Who are your customers?
Typically, there are several interested parties. Typically, when it comes to public transport, we talk about system integrators, which offer bigger depot management systems, and localization is part of these bigger depot management systems. And there are companies well known in Europe and Germany. These are the main customers. But it also appears more and more that the public transport operators make tenders about positioning systems by themselves. So they want to have an independent positioning system. So also the operators will be our customers for public transport. For main rail, it's different. For main rail, we talk both to the train manufacturers, because on their new architectures, they all want to have a highly precise localization. So we sell into train manufacturers, you know, the big ones, but also the operators like Deutsche Bahn have high interest in localization for all those use cases with the depots, with the washing halls, but also having an accurate position on a track. So a broad range of customers, and the interest is increasing more and more.
Then, are your solutions robust enough for the mainline railway? What does your roadmap look like?
Yes, it's a very good question. The whole program started for the field of public transport for buses. And you have seen these tracelet products, and these tracelet products with the plastic housing are intelligent antennas. And these intelligent antennas will go on the roof of a bus, which is fair enough and fully works and is fine for the bus manufacturers. For the railway market, you need to have a more robust solution. And therefore, we are working currently on a device which goes into the railway system, which is more robust and offers, let me say, this will be a device which will be installed within a train, not on the roof, but uses the antennas from the roof of a train. And this one will be available approximately in 9 to 12 months.
Okay, you mean that permanent internet connection is required in the vehicle?
Mm-hmm.
Is that right?
If you would like to use the correction data from an N-trip service provider, then we need a permanent internet connection, because the philosophy is you receive GNSS information, you know you're unsecure, you send your position to a service provider, and the service provider sends you the correction data back, and this needs to be in real time, because you would like to have an accurate position in real time. So yes, if you would like to use that methodology, you have to have a permanent internet connection. If you lose it for once in a while, of course, then you may lose your accuracy for this certain position or for this certain time.
Okay, next question. Several safety applications in the railway sector come to my mind, e.g. position of trackside warning systems, cold movement detection, etc. Would these position information usable without further qualification in a related safety function, e.g. SIL4?
No. A clear no. It can always be only one cornerstone for creating a safe position. Remember, I had this use case for future automated train operation. It can never be the single information somebody relies on in a safety context. The product's not designed according to any safety regulations or safety standards. For now, it's used for these kind of as added value applications, but it can be a future cornerstone for a safe and accurate position.
Okay, next question. Are the position information resilient against spoofing or reflection?
Reflection is something, when I understand the question correctly, is reflection when you are in cities with skyscrapers and things like that, and you have a lot of reflection, then the correction data help. And the also the built-in data reconing functionalities, plausibilities, how your movement can be. Yes, it's resilient against reflections. Against spoofing, it's kind of a question for security. I would think so. Yes, let me say it is. Every position information is, of course, packed into a kind of a protocol, which can be secured also for security reasons. But for the first case, it's not.
Okay. On slide 15, EMU is mentioned as a possible source of data to be merged. How is this addressed by LYVE?
Mm-hmm. So in IMUs, and it's kind of an accelerometer, which allows detection of a movement in any direction. And this one is a very important additional feature because you need to you need always to know how your system can make moves. Let me say a bus has different moving how's the word behavior, a different moving behavior than a train or than maybe a scooter. And therefore you can use an EMO to plausible a movement. Does it make sense what we just saw? Yeah. Can we find out in which direction a train or a car or whatever is moving? And this is all use cases for the EMO, because we simply use the accelerations in all directions also for our sensor fusion.
Okay, then the last question. On which standards the solution is based? Is there a standard used to combine different technologies?
No, for the combination, there is no standard, but the single solutions which we use are standardized. So GNSS, of course, it's standard anyway. It's standardized how the signals and codes are transmitted and so on. The standard how we offload the position is standardized with EGS84. And the standards for ultra-wideband, Thomas will go in detail, are basing on the FIRA standard. Where we also will be fully compliant to. So every little cornerstone is based on standards, and we put them, our solution pretty puts them together in one product.
Okay, then thank you for answering all these questions.
I have just one remark. There are 2 additional questions in the chat, but we have some time issues, and maybe we can ask Matthias to answer the questions directly in the chat. And
Sure.
If we have time after the second presentation, I've collected the questions anyway, and then we might have the chance to answer them within the webinar.
Sure. Thank you so much.
Okay, then thank you. And we will go further to our second speaker. Matthias mentioned him earlier a few times. Second speaker is Dr. Thomas Greichen from the company Pinpoint. He studied electrical engineering at the Chemnitz University of Technology and did also his PhD there. He's one of the founders and managing directors of Pinpoint, and Pinpoint is a spin-off of the Technical University of Chemnitz. And he is also an expert in ultra-wideband based localization. Yeah, in addition, Pinpoint has partnerships with international renowned ultra-wideband chipset manufacturers. So I would say, Thomas, the floor is yours.
Thank you, Rico. Also welcome from my side. As already introduced, my name is Thomas. I start sharing my screen, so hopefully you can see everything.
Yes.
My presentation will focus more on the basics of ultra-wideband to give you some insights there. It also addresses a little bit the previous questions on standards and how we use ultra-wideband for these products. And of course, I also like to focus my presentation on the use case of the positioning of individuals and also the use cases which will be possible by having indoor positions directly on the smartphones. Okay, so let's start. In general, I'd like to ask the question, why are indoor positioning systems for users required? As you see here in this line, probably the most centered use case is the confusion in buildings, in complex buildings such as crowded train stations, crowded airports. You have these situations also in stadiums and shopping malls and so on, where a lot of people like to have a kind of an orientation support or a navigation support. And for this, of course, Matthias already mentioned this, GNSS-based systems are not available, and there's a need for an indoor positioning system. Yeah, if an indoor positioning system is established within these buildings, you can also build up other use cases and other improvements. For instance, from the left-hand side, you see queues. We had requests from customers from the stadium sectors, from football stadiums, where the people are crowding at one entry gate and another entry gate is completely free. So what they want to use navigation at the user also for such use cases, from Google Maps, where you have a visibility on the congestions and can then redirect the people to the free gates. Another use case that we also have is the use case of manual authentication processes. That means this request comes more from the Asian area, where a lot of people are using the public transport, and you really have queues, congestions in this ticket area where you validate the tickets. And their first approaches of using ultra-wideband for an automatic authentication of your ticket is established, and there we can also bring in ultra-wideband for just improving the process and in the end also the user experience. I also have some short video we made at the Consumer Electronics Show 1 year ago in Las Vegas. This is the way navigation today is working. Maybe you just have a look on this and see how people are navigating today. So the conclusion is a lot of people require navigation, but they still use these paper-based building plans where they not really know where they are. You always have to look for the dot on the map, and they also don't know where's the direction I want to head to. And this is, especially in this complex situations, a motivation for indoor navigation systems, where you can improve the overall experience of such a trade show visit. And this is where we'd like to introduce use cases on the phone side. So what can you do? I previously mentioned navigation as a kind of a central use case, but you can also have something like location sharing. So that means if you are in a crowded area, you're looking for your family members or for your friends or for people who want you to meet, then of course you can share your position and can be navigated directly to this position. You can also get directly information based on your surroundings. So building up these augmented reality solutions where you can see additional information directly in the field of view to improve the general usability of the building itself. Yeah, and of course, I also show this in a later or in a future slide here, the delivery to phone use case. So the things you know from Uber Eats and from all these delivery services are now also possible in the indoor environment, where, for instance, you in an airport where you're waiting for your connecting flight can directly order, for instance, a drink or a coffee directly to your place. And this is where we have talks also with customers from renowned airport providers, where they want to extend their indoor services to their passengers by bringing in such a positioning technology. So in the end, we are speaking in kind of a general technology for buildings and for users to provide services, and this is what we as Pinpoint also providing. So now from the technical point of view, just a short visualization why GNSS is not working indoors. The frequency the GNSS satellites are using are prone to shattering and obstacles, and so a ceiling of a building or also the walls of the building leading to a complete shattering of the GNSS signals, so that you cannot use them anymore in the indoor environment. And this is just a short sketch up why you need an indoor system that is installed and planned there to provide a precise position there. Now I'd like to give you an insight on the available technologies. So ultra-wideband is not the first technology to address the use case of indoor positioning, but the previously tried and the previously used technologies doesn't lead to a widespread of indoor positioning. And I'd like to give you a short insight on the technologies available and also what are the drawbacks of them compared to ultra-wideband. So let's start with Bluetooth. Maybe some of you are using or knowing the Bluetooth beacons, which were introduced by Google and Apple. There was the standard iBeacon or Eddystone of Google. They provided these small units, these battery-powered units that you can install in buildings, and they are just beaconing a ping with their ID you can use for positioning. This is a pure received signal strength-based approach. That means a smartphone is sensing the presence of these beacons, also with a received signal strength indicator and the ID, and is using a mapping from the ID to a coordinate of this beacon to calculate its own position. The problem of this approach is that these signal strength-based approaches are very prone to errors and very prone to environmental changes in the building. So in the end, you only achieve accuracies around about 1 to 5 meters with Bluetooth on smartphones. And you also, if you would like to achieve these accuracy, you have to equip your buildings with a huge amount of such beacons. And in the end, you also have to manage these beacons, which can lead to very high maintenance costs and installation costs. So Bluetooth, these are the main reasons why Bluetooth isn't established as a good to use technology for indoor positioning. On the other hand side, there are services and products out there that are just using Wi-Fi. So the given Wi-Fi access points to sense Wi-Fi signals for indoor positioning. The accuracy is even better compared to Bluetooth with 5 to 15 meters. The reason for this is simply that you don't want to roll out a huge amount of Wi-Fi access points due to their price. The only areas where I saw these Wi-Fi based positioning were in shopping malls and in airports, where they use the access points for the huge amount of users to provide them with connectivity and just to use this given infrastructure for positioning. But still, you don't get a precise positioning there. And as another fact is, due to the timing of these Wi-Fi signals, the calculated position on your smartphone doesn't have a high update rate. It has a latency of up to 5 seconds. And this can't be used for live navigation due to the lack of the received positions. Another thing that's more from the industrial sector is the usage of RFID, these near field communication kind of systems, where you have a reader that is receiving, for instance, the ID of these RFID tags of assets and so on. It's more used for the management of objects that are in production. So this is not a technology that can be used for smartphones. There are, of course, some approaches in public buildings where they are mounting QR codes, and all in the QR codes, these NFC tags, where you can, if you are a user, can just either scan the QR code or hold your smartphone next to this unit to get your current position. But this is where you as a user really have to use it in an active way. That means you actively have to scan something to get your position. So this is nothing you can use for a pure passive or for pure guidance by a system that delivers you all the data you require. GPS already mentioned. If you are in a building that has a glass ceiling or that has good visibility to the sky, then of course you could also use GNSS as a positioning service, and you're ready to go. But this is not what you usually have in buildings. Therefore, you just get some smaller signal levels in GNSS. You'll get a position on smartphones based on GPS, but it's very, very poor and cannot be used for live navigation. Another thing that was driven by Philips as an LED producer, it's called VLC, Visual Light Communications. So what is done there? The LEDs are not only illuminating the buildings, they also modulate a kind of a short, non-visible code into the light. And this light or these pulses can be decoded by the smartphones, because the cameras of the smartphones are able to sense these pulses and do the positioning on it. To my knowledge, there is not a widespread distribution of this technology. It was evaluated in some shopping malls and in some shopping malls, but this technology is also prone to occlusion. That means if the user is covering the cameras or you have occlusions by your body, then you don't have line of sight to the LEDs and then cannot do the position calculation. And this is where I'd like to mention ultra-wideband. Ultra-wideband is able to do in the background the positioning based on timing information. So you not only sense the signal strength of the received signals, but you really measure the time of flight of such an ultra-wideband signal. And because ultra-wideband is using a very, very, very wide spectrum, you get a very good time resolution of the time of flight that you can in the end use for a precise position calculation. And this is where the rest of my presentation is heading to, is giving you some insights on ultra-wideband. Why is it good? And what are, compared to the other technologies, are the advantages? In this slide, I'd like to give you a short insight. What is the problem with, again, signal strength signals? You have such a room structure where you have a lot of walls, you have a lot of interiors, and all these interiors of a building are changing the received signal level of a device. For instance, if you are using Bluetooth or Wi-Fi, and this leads to poor positioning results. And this is in the end what ultra-wideband is capable. I show you in the later slides. It's able to also detect line of sight conditions. It is also because the received signal strength isn't really evaluated for the positioning. It doesn't change, or the runtime of the signal doesn't really change based on the change of interiors, and so it's more robust and more reliable than the other technologies. So some basics also on the ultra-wideband level side. The frequencies that are used, you see Bluetooth, Wi-Fi, and so on, are mainly used at 2.4 gigahertz. It has a narrow band here, so that means you don't really have the bandwidth to do precise time measurements. And this is what ultra-wideband is really doing. For instance, it takes a 500 megahertz wideband at 6.5 gigahertz, or for instance 8 gigahertz, and using there the wide spectrum to do the precise time measurements. And this is what you see here. Narrow band has, if you look in the timing area, you have these the edges of the signals are not really perpendicular to the time. So the sensing of really a time moment isn't so easy like you can do this when you're doing this with ultra-wideband, because there you really have a very, very narrow edge here. And this leads really to a precise time measurement. So which procedures or which algorithms can be used to do an ultra-wideband based positioning? So the anchors, or the satellites, we called them in the previous part of the presentation, are having well-known positions. So you know the X, Y, Z coordinates of them. And the tag is the unit that needs to be positioned. And the first approach is the so-called two-ray ranging. That means a tag is determining each distance to an anchor, and based on the pairs of, or based on these distance information, you can do a positioning or position calculation based on a multilateration approach. What is this leads to good positions, but what is the general drawback of this approach? The general drawback is that the tag needs to actively communicate with each and every anchor, and are occupying the air interface. So in case you have a lot of tags in your environments, so for instance, hundreds of cars or thousands of users, you simply do not have the capacity in the air interface for the communication of all these tags. And so this isn't really a scalable solution. To address the scalability thing, there could be used another approach that's called uplink TDOA, or uplink time difference of arrival. In this moment, the tag isn't doing a pairwise communication with the anchors. It's just doing a ping, a very, very short one. And this ping is received by synchronized anchors, so that they know when this ping is receiving at their place. And based on the time difference of the signal arrivals, you can do the position calculation. This leads to a better scalability of the solution. That means you can scale up the amount of tags in your environment. Also, the tag isn't using so much energy anymore, because it's only doing a very short ping and that's it. And the position calculation is performed in the infrastructure. That means on a location engine on a server or something like this. But you have also some other drawbacks. This approach relies on a very, very precise synchronization, time synchronization of these anchors, because the position quality, or the quality of the position of this tag, is relying on a nanosecond precise synchronization of all these anchors. So you have to, in the end, you have to take care of this synchronization, and this leads to a bigger system complexity. At this moment, I'd like to introduce then the downlink TDOA. That's the reverse direction. That's important for the smartphone use case, where you want to ensure that your users have the position, like in a GNSS approach, directly on their devices. And you also want to have a kind of a privacy by design approach, where the infrastructure, or where the servers are not knowing the position of the tags. And this is what we at Pinpoint are doing. We are having the anchors only broadcasting their position and time information, and we have a location engine directly on the tag, which is capable of receiving all these information and doing directly the positioning on device. And so you have addressed these privacy issues, and then as a nice side effect is, because only the anchors are broadcasting, you can, in practical scenarios, you can scale up the amount of tags in an indefinite way. So if you are in stadiums or airports with very crowded areas with thousands of people, the system is capable of providing, the position information. At this moment, I'd like to address one of the previous questions, which standards are established in the ultra-wideband sector. So as I'd like to show you at the beginning here, there's a standard on the physical layer. There's an IEEE standard who's defining which frequency, which codings and so on are used in ultra-wideband. All these standards here, or these different standards of IEEE, are addressed by the generally available chipsets, ultra-wideband chipsets. So that's very important, because you then can mix up systems where you have, for instance, satellites with an NXP chip and text with a Corvo chip. And it's also important if you have an environment where your users are using different smartphones with different chipsets. They, in the end, really want to use the same device with different infrastructures. And on top of this IEEE standards, there are different standards that are addressing different use cases. So the industrial side is covered by the OMLOG standard. That's mainly for the use case of asset tracking, industrial processes, where you need a high reliability of the position information, where you want to build up a homogeneous infrastructure. On the left-hand side, you have the FIRA standards. That's for the end user devices, smartphone infrastructures, and so on. So access points will use this FIRA standard, but also the smartphones, to have an interoperability between the devices. And the third big standard is the Car Connectivity Consortium standard, which is using ultra-wideband for the car access control. So popular use cases or popular announcements are, for instance, from BMW, who are digitizing their keys within the wallets of the smartphones, and you can then use your digitized digital key for opening and controlling your car. So you don't need your physical keys anymore. You can directly use your smartphone. That's what's going up in the standard sector. Here's just a quick overview. What is the distribution of ultra-wideband and phones? So generally, Apple is introduced in 2019 the ultra-wideband in their phones and in all their devices. So the Apple world already coped completely with the technology. On the Android side, it's a little bit slower. So this is ultra-wideband is there still a premium feature, but this is changing this year, because at the Mobile World Congress, the world's biggest trade show on the mobile sector, Qualcomm, as a major player in the chipset area of phones, announced also an ultra-wideband Bluetooth Wi-Fi combined chipset. And this chipset is now integrated in nearly all upcoming Qualcomm-powered Android devices. And so we expect that ultra-wideband is covered by much more devices than in the past years. So what about Pinpoint and how we are doing this downlink TDOA? So what we have is we're having ultra-wideband anchors. These anchors are providing the broadcasted signals directly to the phone. The phone needs, of course, an ultra-wideband chip to receive these signals, and then can do directly on device based on these signals with our positioning engine, the position calculation. And then we provide software development kits so that app providers or also for other environments to use the calculated position for the services. I'd like to give you here a short overview. These are our building satellites. This is clean indoor variant. There's also an IP65 variant for the train and the rail sector. And These satellites are providing the signals, and for instance, you can use a smartphone to receive this position, or this is the car tracking unit from the CI4Rail. There's an ultra-wideband chip with our firmware integrated to do directly the positioning here, and then you can either use the device directly on the device, or you can use any Wi-Fi or any wireless connection to broadcast the position or to direct the position, for instance, to a server or to a management system. Which products variants we provide? We have the satellites, we have some batch devices that can be used with Bluetooth connection to extend the functionality of standards smartphones without ultra-wideband directly with our technology. And this is our mainly intended business, is that we are providing the ultra-wideband modules with our firmware for integration in other devices. So for instance, as already mentioned, CI4Rail is integrating such a chipset in their car tracking unit to have the indoor positioning directly on board. And for bigger companies, it's also possible to license our firmware to directly bring the Pinpoint technology directly on an ultra-wideband chipset. That's just for interested people. What is the entry into the Pinpoint world? You can just get started with a prototyping kit where you get the satellites, also some positioning devices, and a prepared Google Pixel 6 Pro with all the technology, so that you can use also our tools in this kit to set up your own environment with positioning services and go directly into the prototyping of own products based on indoor position data. Due to time, I'd like to skip this video. I just have another video for you. We are doing also some POCs with the Deutsche Bahn based on the navigation services. So this is a POC where the satellites are installed within a train so that you can get a navigation directly to a reserved seat within the train. That's all. And I'm also at the end of my presentation. Thank you for listening. As Matthias already mentioned, we are exhibiting also in Nuremberg at the Embedded World together with our ultra-wideband chipset supplier Corvo and another company. So in case you are at the Embedded World, we would be happy if you join us there to just also have a touch on the technology. So there will be also a live demonstration. That means we will equip a bigger booth also with our technology so that you can directly experience the technology at our place there. And of course, that's also important. We also have a booth at the InnoTrans in September. So if you also joining the InnoTrans, we are happy to see you there. Thank you.
Then thank you very much. I think also here we go straight to the Q&A. So far we have 2 questions. Please, when you have more, write it in the chat. The first question, when is ultra-wideband positioning generally available in common buildings?
To answer this question, it's necessary to understand what's going on the standardization side. So last year in November, the FIRA consortium published the so-called FIRA 2.0 standard. This is really the GPS mode we are also pushing, and we expect that, and we see in our network that bigger access point manufacturers are integrating ultra-wideband with this new standard into their products. So what I expect is that by end of the year, there will be these building hardware available. And so beginning from next year, we will see the ultra-wideband based indoor positioning for smartphones in the new or in the bigger buildings.
Okay. Which role plays the big smartphone vendors such as Google and Apple?
Yeah, these are the gatekeepers for the smartphone side. So they are publishing the interfaces to the app developers and also taking care of how do they provide position services to app developers and service providers. And they also started 2 years ago to provide software development kits for Ultra-Wideband. They will also open this for the Sphera 2.0 standard. We see this already in the sources, in the source code of the operational systems. And yeah, so when they also open the gates for the new standard, then there's nothing that that speaks against a widespreading of this technology. Rico, you're muted or the audio is disturbed.
Sorry. Is there any further questions from the audience?
Not for the moment. There was only a remark of one of the participants. He said that, or she said that we also have a solution in CO2 quality, which RTK at prototype level. Maybe this webinar is a chance to get some new context between you as presenters and you as the audience. For sure, we will exchange all the contact data of both speakers, and everyone has the chance to directly contact these the speakers. And I think it is one of the goals of ERCI webinars to establish new contacts for new developments, for innovative solutions, and so on. And for sure, you are kindly invited to get in contact to the speakers. Then we had two further questions from the first presentations. I will show them, and they are already answered in the chat. And if you have a look into the chat, I hope that the answers of Matthias are sufficient to you. So,
if not, please contact me.
Yeah, otherwise it's the same possibility to contact the speakers. So I will overtake this session now. My name is Lutz Hübner from the Berlin-Brandenburg cluster of transport, mobility and logistics, also a member of the European Railway Clusters Initiative. And I want to invite you, all of you, to take part in our short survey on this webinar. How do you felt? How did you like the webinar? How did you like the presentations? And what suggestions do you have for future topics for upcoming ERCI webinars? We already have prepared a list on that, which I will show you later. Let me introduce to you some activities with ERCI clusters are taking part in it and might be of interest to you. There is the Success project. It is to support European SMEs for the rail supply industry successfully applying to public procurements in USA, Canada, and Norway. And therefore, there is a special service to you established by the project. Weekly, there are available so-called Tenders Watch newsletters. And if you are interested to establish a business in these three countries and to contribute to public procurements, you are kindly invited to contact Ms. Irina Vescu or Ms. Garazi Carranza Luisaga or Miss Amelie Espirou to subscribe for these Tenders Watch newsletters is free of charge, and maybe it's of interest to you. Then we have the B2B meeting platform coming from the already finished STARS project. It is mainly on matching companies of the rail supply industry with solution providers Let's support them in adopting advanced technologies to improve products, services, manufacturing processes, and organization. It's a permanent platform. It's open until 30th of September 2025. And you could make use of them to find new interesting contacts by setting up a short profile on this platform, tell you where you are, which services or which products you can provide, and maybe you find some interesting partners to discuss with them. So then, for sure, our webinar will be recorded and will be available in some few days at the STARS YouTube platform, as every webinar in the near past has been published there. That means you can see this webinar, the recording, in a few days. Yeah, let me introduce you to one project ERCI is leading. It's a Europe's Rail project called LEADER 2030, Learnings for European Autonomy to Deliver Europe's Rail in 2030. The main contact is Guido Ankarani. He is the operations director of ERCI. And the project partners are, beside ERCI, the Geo-Competence Center in Freiberg in Saxony in Germany, then the French Technology Center Relanium, and the Turkish Technology Center Technopark Istanbul. And if you see how many components are needed to produce a pencil and where they are from, you can already imagine what affects a gap in supply chain for raw materials for the railway sector will implicate. And this project is to find the gaps and to recommend mitigation measures to close the gaps. The key words of this call are supply chain needs of the future, supply constraints, risk of supply availabilities to deliver EU rail innovations, and strategic options to ensure resilient solutions and autonomy within Europe. And one of the key words is innovation. And so for innovation, also kind of raw materials are necessary for the rail sector, and that is the project about. So there are several geopolitical factors in climate change which can cause in gaps or in disturbances of supply chains for raw materials for the rail sector, and the project has to make an investigation what are the main factors of this situation. I already introduced you the project partners of this project, and this is the agenda of the project. The first is a study of the past to identify alerts for the future. And for studying the past, all rail-related companies, startups, small, medium-sized enterprises, suppliers, mid-caps, OEMs, operators, infrastructure managers are invited to contribute to a survey which goal is to investigate what are the gaps of in the supply chain for raw materials for the railway sector. You can find these European consultation on these disruptions in several language versions. These are the languages of the ERCI clusters. It's in English, in German, in Spanish, in French, in Italian, and in Polish, Swedish, Serbo-Croatian, and Turkish. available. If you are not familiar at one of these questions, please use the English version, and your contribution as a company is very fruitful and valuable for defining mitigation measures to overcome these disruptions in rail supply chains. Thank you for contribution on that survey. Coming to topics of next ERCI webinars we will have a webinar in the near future on the topic of digital twin, on railway international tenders, on monitoring and inspection of rail infrastructure, of human factors and AI, of cybersecurity and freight of logistics. The dates are not clear for the moment. For sure, we will at least have one webinar after the Easter break in April. In April, and our goal is to have each month one ERCI webinar. Maybe not in August, because in August is the big summer break. So if you have additional topics to propose, please let us know by filling in our short feedback questionnaire. And for sure, we keep you informed on these on the future timetable of ERCI webinars. For today, thank you very much for your contribution, for your participation, and for the speakers for the interesting presentation. Have a nice day and see you soon. Bye-bye.